How are we doing today? Doing all right. Wonderful. Okay. I hope that I have all of my technology stuff ironed out. The projector was the wrong resolution, and then that messed up my tablet program. Uh, Things seem to be in order now, so uh, let's get going here. Okay, so we have 5 lectures left. 3 this week and 2 next week, I think. So what we're going to do is this week we are going to finish new material for chapter 16. Okay. We have one section that we kind of barely introduced uh, last week, and then we'll talk a little bit more about that today. And then the last 2 sections have to do with 2 major theorems that are going to pull together the chapter 16 information. Then, for the lectures that we have the following week, those will be review days in preparation for our final exam. The exact dates for the final exam, I don't remember offhand. Huh? Was that the Wednesday or the Monday? Okay, I thought it was the Wednesday. And then, yeah, it'll be at a slightly different time than normal class time. I don't remember if it's, I think, is it the 10 o'clock block? I'm trying to remember. Oh no, it's 9. Okay, that's right. I forgot. They start at 7 because they don't want to give finals on Friday anymore. What? Ugh. Okay, all right. I don't want to get into the details of the question that was asked, which is if the final is comprehensive. The final is going to be focused on chapter 16, okay? But chapter 16 subsumes the skills of the rest of the course. So it's going to be a comprehensive final because that's how chapter 16 works. Now, if there are specific special topics that we need to be aware of, like equations of planes or something like that, because it's going to tie into particular questions I'm going to ask, I'll throw you some bones in terms of like helping you prepare for those kinds of things. But you should be thinking about it as if it's a comprehensive final, because in chapter 16 we have to use everything. Okay. All right. Sorry. First day back. I got waylaid by that question a little bit. Anyway, we're like, it's like we show up, immediate panic. All right. No, I know. I'm kidding. I'm just giving you a hard time. I get it. It's completely completely fair thing to ask about. It's only 2 weeks away. Um, all right. Probably also you can tell that I haven't written the test yet. I'll do that later. Anyway, so surface integrals. All right. So the basic idea is that if we have some kind of surface that is in space, okay. Now, like this thing is curved, but I don't want to confuse people by trying to make it too curvy because I can't draw that well. But this thing's not flat. Okay. All right. What we would like to do is I want to be able to pick a point on this surface, okay, and be able to figure out what's going on with it. All right. Now, if we imagine for simplicity that the domain below is a rectangle, okay, then this point up here corresponds to a point below on the domain, okay? The version of the picture that I'm drawing is the version of the picture that is a graph, okay? It is not necessarily the case that we always have a graph here, but this is the one that makes the thing the easiest to understand, okay? So instead of writing x and y, I'm going to write u and v here, because for a general surface, the rectangle below is going to be, or it may not necessarily be a rectangle, but the parameter domain is going to be not necessarily the xy plane. Okay, so we have some expression here, but the idea is that I'm looking at some dot here, and I want to investigate the patch that corresponds to that location. All right. Now, this patch is going to correspond to a patch on the surface. Okay. And what I want to do is I want to be able to integrate in the parameter domain with respect to the surface. Okay, so I want to integrate with respect to u and v, and I want to understand how that works with respect to the surface. Okay, if we zoom in on this picture, on a little part of the surface, what we have is a vector here in the u direction, a vector here in the v direction. Okay, and the surface is curving, but there is a flat parallelogram. I'm really trying to make this a parallelogram. Okay. All right. The surface is curved. That parallelogram is flat. All right. The area of that parallelogram is given to me by this expression. Okay. R is the parameterization of the surface with respect to u and v. All right. And r partial u and r partial v are the partial derivatives of that representation with respect to the parameter variables. We know all the way back from chapter 12, as the idea of a comprehensive final was brought up, that the area of a parallelogram is given by the absolute value of the cross products of the two component vectors that form the parallelogram. So this vector is one edge of the parallelogram. This vector is the edge of the other part. Okay, if I take the cross product of those two vectors, take the absolute value, I get the area of the parallelogram. All right, so when we talk about integrating with respect to the surface, this is what we mean. Okay, what I want to do is, instead of thinking about a bunch of infinitesimal patches like this, like normally we had rectangles, right? And then when we started switching to different coordinate systems, we had little deformed patches that we would use. We had polar rectangles for polar coordinates. We had polar rectangles that had height when we talked about cylindrical coordinates. And then we have little spherical sectors that we used when we went to spherical coordinates, right? Okay, this is an extension of the same idea, except now we're looking at the little parallelogram patches and using that as our differential area element. So this term is going to show up whenever we write down a surface integral. When I use the notation, the integral with respect to the surface of some scalar function, f of x, y, z, ds, and that's a capital S, this is equal to the integral over d. This is the integration domain, and this is the surface of f parameterized with respect to the variables u and v. And we get this term here, dA. All right, does that make sense? Okay, so short version of the story is when you see ds, change it to this, because this is the thing that you can compute. But know that a lot of the formulas are written using the much more condensed notation because mathematicians are lazy, right? And it is important to understand contextually that not all of the ideas of calculus were discovered or studied in a logical order, okay, the order that we would describe things in a textbook nowadays. They were discovered or worked on independently and then brought together and then reworked 3 or 4 times because people who were solving very, very hard problems realized there were some issues with the way that the very deep underlying mechanics of calculus works, so they started to change things. But we have several hundred years of old notation that have been kind of kept, right? It's like an old building, you know? Like you don't tear it down every 10 years and then rebuild it with all the new stuff, right? You end up with places that still have copper pipes and lead in the paint and asbestos in the insulation and all that stuff, right? It's the same kind of thing. Now, I'm not saying that this is all dangerous, but it's where we are. Okay. This should remind you of this. Okay. This is the expression for the integral with respect to arc length. Okay, lowercase s here. And we see that there is a pretty large similarity between these two expressions, right? Here we have a special type of way that we're measuring when we do our integration. And here we have an expression that involves a parameterization and a way to figure out the magnitude of that parameterization. Okay? This here is measuring the moving parallelogram as we integrate over our domain with respect to area, right? This is measuring the length of the tangent vector as we move along a space curve. Okay? This integrates by measuring velocity. Well, speed technically, but we're integrating by measuring what the instantaneous speed is everywhere. Okay? This is measuring by looking at how the area is deforming as we move through the domain. Okay? So if we draw this picture, I have a vector that at different points will have different lengths. Right? Here it's slowing down and getting shorter, and then it speeds up. It's probably short again here, and so on. Right? The tangent vector at each of those points. Okay? If we look at this case, then we have some kind of surface, And what we're going to have is at different points, different size parallelograms based on what the derivative is. Now, I can't draw this picture as well, but we're imagining these sitting at each one of those spots. Okay? And as I move around and how big u and v are, I'm going to get longer and shorter vectors, and that's going to change the size of the parallelogram. And that's how I measure in this regard. Okay? It's helpful if you can see these things because it makes you less likely to make a mistake. Otherwise, you're stuck with the formalism, right? You treat the formalism as a tool, and the pictures as something that are helpful. Okay? Now, another idea to keep in mind with this picture is that also at each of these points, because we have these vectors here, there's a cross product, right? So I have a normal vector to the surface. Yeah? That's actually what we're measuring with respect to. This is the magnitude of the normal vector. This is the magnitude of the tangent vector. Okay? So what I have is I have a vector that moves along, just like in this picture, and I'm integrating with respect to the length of that vector. Okay? Here, the patches make the area idea easier to see. But what I'm really integrating with respect to is those normal vectors as it moves along the surface. Okay? Now, integrating with respect to these vectors is what's going to make the material from the next two sections make the most sense. Okay? Anyway, that's why I'm spending all this time talking about this. Okay, so I want to pause for a second here. Do these pictures and ideas seem sensible? Okay? This is the part of Calc 3 that kind of at the end of the semester, I think a lot of people just, like, your brain's full and you're done. You see the finish line, and it's just like, I have to get a B on this next test, and I don't care about doing anything other than that, or whatever's going to happen, right? Don't do that to yourselves, okay? This, getting to this point and really being able to grok this will pull in the rest of the class and make things easier to remember, okay? All right. Okie dokie. So let's do an example, and then we'll talk about oriented surfaces. I'm probably going to need a new page for this. Okay, this is an example from the textbook. So we're integrating with respect to S. We're going to integrate Z. All right. Okay, so on one part of it, we have the cylinder here. On another part, We have the disk. Okay. So we have three elements here. We have a cylinder around the edge. We have a bottom, which is a disc, and then the top, which is a slanted cut. So if we make a sketch, it's going to look like this. The bottom is a circle. We have a cylinder up here, and then we have the edge of the cylinder come down. So imagine a paper towel roll, and I slice it at an angle. So this part here is S3. Okay, this part here is that, and this part here is S2, sorry. And then for S2, we should also specify that this is z equals 0. It's in the circle, the disk is in the XY plane. All right, so the S1 is the entire cylinder, like the entire infinite cylinder. It goes on forever in both directions, right? Unless we put some restriction on Z, okay? And the other two surfaces, S2 and S3, truncate it. So S2 slices it down here at Z equals 0 and fills in the bottom. And then the plane comes in this way and cuts it. Yeah, there's a picture of it in the textbook that is better drawn than the one that I have. But that's what's going on. And then just so I say it so it's clear, the way that this plane cuts is this reduces to a point down on one of the edges. All right, anyway, thank you for the question there. It helped me clarify something that I wasn't done as well as it should have. Okay. All right. Now, this, okay, so we're looking at the expression here, okay, and we want to integrate over the surface. The issue is that we really have three different segments for the surface, okay? And if we want to integrate over the entire surface of this object, it's going to be necessary for us to do each piece, right? So the way that we're going to attack this problem is by doing the integrals for each of the segments individually, okay? So if I'm looking at the integral over S of z ds, what this really is, it's the integral over S1 plus the integral over S2 plus the integral over S3. All right. So There isn't a nice way to do this part. Okay, it's just how it goes. Now, it is important to know that because we've broken up the problem into different elements, there isn't any. We don't have to do each of these the same way. Okay, for instance, S1 is pretty clearly a portion of a cylinder, right? So we can use cylindrical coordinates in order to do that integration, and things should be fine, right? Or a parameterization that's going to remind us of cylindrical coordinates. Okay, and then the other parts are going to be handled probably using polar coordinates or something similar. All right, so let's do this. We got S1 here, all right? We need to parameterize this shape. I'll fill in the part we care about, okay? We know that it's a cylinder, right? That's cut, okay? So my x and y values are always going to be on this circle, right? And then I'm going to have a height, okay? So the parameterization that we're going to use here is basically cylindrical coordinates. Huh? R is 1. But yes. We know that R is 1 because we know the radius of that circle. Okay? So that's not so bad. Now, we have to make sure that we understand what the ranges are for our parameters. Okay? Theta is going to go from 0 to 2 pi. We need to go all the way around the circle. Okay? And Z is the tricky one because we have to go from the bottom here to this upper part, right? Okay, so we're integrating from z equals 0 to z equals 1 plus x. We'll write it like this. Now, writing x here doesn't do us any good. So we'll write it in terms of our parameterization. All right. Now, the other thing that we need to do, because we're integrating with respect to the surface, is find this expression. Sorry. I'm going to hold off the absolute value signs for now. And so we need, because we're computing a cross product, we write our ijk, and then we want the integral the derivative of r with respect to theta. So we're going to get negative sine cosine 0. And then we want to differentiate these again with respect to z. We're going to get 0, 0, and 1. Okay. We compute the cross product using determinant by minors. This is going to be cosine for the I part. This is going to be positive sign for the j part because there's a minus sign here, and then this is 0. I looks suspiciously like a j. Let me fix that. Looks like this, right? Okay, now if I want the magnitude of this, the square root of the sum of the components squared is 1. Okay? Now, calling back to what someone asked about earlier, does this make sense? Yes, because the Jacobian for cylindrical coordinates is r dz dr d theta. R is 1 because we have a circle of radius 1. If we had a circle that was a different radius, the value that we should get from this, because we're using something that's basically cylindrical coordinates, should be whatever that fixed radius is. Make sense? Okay, so we have that. We're ready to go here. Now we can write out our integral. The double integral with respect to S1 of z ds is given by the integral over the domain of z times the magnitude of r theta cross rz dA, and this, putting in our limits of integration, is going to go from 0 to 2 pi and from 0 to 1 plus cosine theta of z times 1 dz d theta. So we integrate z. If we really want to be picky about it, we can also immediately notice that this integral is separable. Okay, so we factor out the d theta integral, and we'll go ahead and integrate the other one because it's easy to do. It's just z squared over 2, evaluated from 0 to 1 plus cosine. Oh, sorry, they're not separable. Whoops. My mistake. The limits have to be rectangular. I was going too fast. All right, apologies for that. Okay, anyway, the z integral is still easy. The theta integral got harder, though. All right, so we have a 1/2 that we can take to the outside. We have 1 plus cosine quantity squared d theta to integrate. We expand this expression. This is a plus b quantity squared, right? So it's a squared plus 2ab plus b squared. So we get 1 squared, which is 1, plus 2 times 1 times cosine, plus cosine squared. All right. Now, what we need to do is these we can both integrate easily. This one we have to use a trig formula for, trig identity. So we replace cosine squared with 1/2 times the quantity 1 plus cosine 2 theta. And now we can integrate term by term. I'm going to combine these. So we have 3/2 times theta. And then we have sine theta. And plus 1/4 sine 2 theta. Oh, I just made a copy mistake. Thank you. I lost this too. Thank you. All right. There's a 2 there. I wasn't tracking that term nearly as carefully as I should have because it's going to be 0. But anyway, thanks for catching that. So, as I just joked about, you plug 2 pi in the sine, you're going to get 0. You're going to get 0 here. You plug 0 into sine, you get 0. So everything dies except for this. And you're left with 3 pi halves for that segment in the integral. Okay, 1 down. So 2 pi, 2 divides out with the denominator, and I have an extra factor of 2, which is how I get 3/2. And then sine of any multiple of 2 pi is going to be 0. So that's what we have for here. All right, next up, we have the double integral for S2 of ZDS. This is the one in the plane, right? What plane are we in? The xy plane. The equation of the xy plane is z equals 0. 2 down. We like that one. That one's easy. All right. So geometry helps us out here. All right. And then for the third one, we need to do a little bit more stuff here. Now, this is the one where we have the plane z equals 1 plus x. Okay? So this one, we're going to want to just use regular polar coordinates because we have to integrate over the whole disk. We're doing this part now, right? That lies above the unit disk, so we're going to use polar coordinates. Z is equal to 1 plus x. All right. X in polar coordinates is r cosine theta. So we make that substitution. And then we also need the to do the coordinate change part of this as well. So we use the parameterization, and because we're using 1 plus x here, I can write the version of ds that looks like this. When we have the graph, right, we have a shortcut to the absolute value of rx cross ry. So it looks like this. This is the formula for z. Okay. This is obviously 1, this is 1, and this is 0. The derivative of 1 plus x with respect to x is 1. Derivative of 1 plus x with respect to y is 0. So we get this. And so that gives us the double integral over S3 of 1 plus x times the square root of 2 dA. And now after we do this part, we convert to polar. Okay. Zero to 2 pi, 0 to 1. We have a square root of 2 here. 1 plus r cosine theta, replacing x, r d theta. All right, now we work our way through this integral here. With a square root of 2 on the outside. Integral from 0 to 2 pi, integral from 0 to 1 of r plus r squared cosine theta. Dr d theta. Integrate with respect to r. Yeah, so the reason that I know it's 0 to 1 is because going all the way back to here, S is the part of this plane that's above the unit disk. So that's how I know. It's a circle of radius 1. It's the entire, it's the disk of radius 1. I use the word disk because it's filled in. So remember, in cylindrical coordinates, the way that this works is we have some kind of circular domain in the plane, and then we look at the stuff that's above it. Okay? And since this thing is slanted, sitting above a circle, that's why we're using cylindrical coordinates and integrating over a circle. Yeah, yeah, yeah. We're projecting it down onto a disk is another way to think about it. If you just like, I don't know, had a thump block or something and just went whatever that noise is, right? From Mario, flattened it completely straight down, doesn't get squished, it just gets smashed. All right. So square root of 2 times the integral from 0 to 2 pi, and then we're integrating with respect to r, so we have r squared over 2 plus r cubed over 3 cosine theta, evaluated from 0 to 1, d theta. So we have the square root of 2 integral from 0 to 2 pi of 1/2 plus 1/3 cosine d theta. And we integrate term by term again. Here we're going to get theta over 2 plus 1/3 sine theta, evaluated from 0 to 2 pi. So we're going to get the square root of 2 times pi. Is all that survives in that interior. And so what we can say is that the integral of z ds is equal to the integral over the components and so we get 3 pi halves plus 0 plus the square root of 2 pi. And you can factor out the pi. Whew. A little bit of work. It's not so bad, though. Okay, now, one of the things that we've seen a couple of times, including the example that we did, I know, a long time ago, before break, but one of the ways that we attack domains that are less convenient is we will chain together our tricks, okay? We'll choose a parameterization that will make a part of the problem easier, and then rather than just doing that one change and then following through with what otherwise might be a difficult problem, if I can look at it and then after a change notice that a second coordinate change will make the problem even easier than what it was, that's what we do. Okay, changing coordinates is easier than dealing with difficult integrands. So there's kind of a puzzle element to figuring out what's going on in terms of looking at what you're doing and understanding the problem and having a big and well-developed enough bag of tools to be able to say, I'm going to pick the right tool for the job. Okay? And it's more about having the experience and the practice and the consistency in correctly solving problems to be able to pivot. Okay? I'm not the reason why I'm able to do this well, okay, and not make very many mistakes is because I have trained myself to be able to constantly try to find the easiest path to the solution. Okay? It's not that I have greatly beyond your capabilities ability to do this. I just have more practice at figuring out what the best way to do the problem is. All right? Because you are at the point now to where we don't really spend I kept taking math classes, but we didn't spend time figuring out how to solve even harder integrals. Okay? We don't spend any time doing that. All right? What we do is spend our time trying to figure out, okay, what's the clever coordinate change to give me an easy as possible domain in which to examine the problem. Okay. Before we take off today, there's one last thing that I want you to look at from the textbook. It's the last couple pages of section 16.7. All right? It ties back to the idea that we were talking about beforehand and the idea of oriented surfaces. I drew the picture before of having a surface and talked about how we want to think about integrating with respect to normal vectors, right? Okay, now our integration schemes are actually going to care about what's going on with these orientations of the surface, all right? It's going to turn out that the way that we want to do this most of the time is to imagine that I have a boundary in which I'm moving around the boundary counterclockwise. Okay? If you use the right hand rule as you travel along counterclockwise along the surface, okay, with your index finger pointing in the direction of the orange arrows, you will find that your middle finger points towards the inside of the domain and your thumb points up. Okay? That is the convention that we choose for positive and will feed into what we're talking about in the following two sections. Okay? And so this idea is going to be very important, and also make it to where sometimes we don't have to do those weird multi-step problems like we just did. Maybe there's a really powerful theorem that allows us to say something about the surface integral if we know what's going on with the volume integral. Okay? Or stuff like that. Anyway, so that's what we'll be talking about next time. Have a good one. I'll see you later.